I snuck it in, so I'm okay.
Do you have any announcements that we aren't aware of?
So the only announcement is that I had a couple mics turned on, so be aware, that they're going on to Zoom, and I'll turn the recording on. You just did? Okay. And we'll make sure we turn it off for the private session, and we can get started. There's bagels, coffee, donuts in the back. So without further ado, we'll get started. Today we're going to talk about magnetic manipulation of unknown non-magnetic objects. So why do we need to think about this problem? Or why do we think about this? So there's this problem that we kind of as a society have created for ourselves, which is space debris. We keep launching rockets into space with satellites that are designed to last, a certain amount of time, and then just to be floating up there, often either for decades, centuries, or until the Earth explodes. So this is sort of a problem we're creating where we're building this net around the Earth. Every obstacle is just another thing we have to avoid. When the pieces of debris hit each other, they create additional pieces of debris. They're smaller and smaller, but when you're traveling at high speeds, the size is not that important. So currently how we schedule launches is we time when we're going to avoid specific pieces of debris, and it'd be better if we could actively remove some of this. There's this, so it's all tumbling, and so think of it as it's like spinning, and not particularly quickly. So here is, sort of a slow video of, this piece of debris, and you have some mission you'd like to be able to grab this piece of debris. But if you try to use a robot arm, it's too dangerous. The robot arm might reach out and grab the debris and either break the robot or break the debris into further pieces. It's the same problem when they collide with each other. Any contact method has the chance of creating additional debris or breaking your robotic system. What we would really like is a tractor beam. We'd like to, without touching it, magically reach out to an object, arrest its rotation, and simultaneously pull it into some sort of central area so we can either grab it again with a manipulator or put it directly into some sort of trash bin, sort of one piece at a time. This would be our goal. So that's sort of our motivation. And to kind of talk about how we've been progressing in this direction, we're going to recap the work from my proposal on magnetic manipulation of non-magnetic objects, specifically two parts. One of non-magnetic spheres, how we began the project, and the second on how we can use adaptive control to manipulate non-spheric objects by just assuming they are spheres. Then we're going to go on to we're building on some recent interesting work where we're going to do adaptive manipulation, but instead of having one sphere we think an object is acting like, we're going to build a distribution of possible spheres that it could be. It's not just a point of it's this radius and this conductivity. It could be any of this set of spheres. And then lastly, we're going to kind of build in that direction, think about this algorithm of Stein variational gradient descent and how we can apply it to a wider variety of robotic tasks. So it's kind of cool that magnets let us manipulate things without contact. This is some previous work from the lab on controlling this magnetic sphere with a stationary electromagnet and controlling its position to solve this children's toy. And so this is the kind of thing we would like to be able to do with the piece of debris in space. But there's a problem. The space debris, by and large, is non-magnetic. What it is conductive. Most of it is either aluminum or titanium. And it's sort of interesting, they estimate this based off the density of the material in space, because we don't necessarily know everything we've launched, other countries have launched over the decades, but we can estimate based off the density of the things in space, how they move, what they might be made of. And these materials, aluminum and titanium, are significantly electrically conductive with respect to non-conductive material. And things that are conductive, we can actually induce force and torques on them by a dynamic magnetic field. So in this image, we have a sliding magnetic field. So we have some magnets sliding along a conductive material labeled C, and the magnetic fields from the green arrows, the magnetic source, it creates what we call eddy currents, which is electrons moving along the surface of the conductive material. Those eddy currents create their own electric field, shown in blue, and those two fields interact with each other, inducing force and torque on the conductive material. So if the magnet is stationary, there's no force and torque, which is what you expect when you just put a magnet next to a piece of aluminum. But once you start moving the magnet, you start to create force and torque. In our case, the way we think of this dynamic field is with rotation. So this is a jig from when we were doing data collection to build a model. And so here is this cubic magnet spinning near a copper sphere. Just again, think of how we would induce these eddy currents. We built this magnetic experimentation setup where we have a copper sphere inside a plastic raft on the surface of water in a water tank, where the objects can, with low friction and without thinking too much about gravity, we can slide along the surface of the water and rotate in place. So we have a 3 degree of freedom simulation environment. And then the way we do it is with 4 of these electromagnets underneath the tank. Each electromagnet that we call here is actually 3 mutually orthogonal magnets that lets us induce an arbitrary magnetic dipole. And if we can induce an arbitrary dipole, we can change that arbitrary dipole, and then we can mimic a rotating magnetic field. So the first part of this work was done heavily in collaboration with Dr. Lan Pham, who's here with us. And so this is the work that we published in Nature, as previously stated. And so her work was building a model of the force and torque induced by rotating a magnet near near a solid sphere. And I'm just going to give you a heads up. I'm going to show you the equation for this model. The only thing you need to take away from it is highly non-trivial. So here is the equation of the force and torque induced from you rotating a magnet near a copper sphere. And the part I'll point out is that this term is to the power of this term, which is also to another power. This would be incredibly difficult to invert. So instead, we use optimization to find if we have a desired force and torque, what control action, what dipole rotation would get the closest to that desired force and torque. And that is this optimization problem here, desired force and torque with expected force and torque, given the constraints that we have on the maximum power we can send to the magnets, on the selection of dipole axes, as well as, importantly, which magnet we're using, because we only have a model of how individual magnets rotating interact with the objects. So we built this control system. So we have some desired trajectory, which then sends desired state to a PD controller, and which sends desired control, think force and torque, to an optimization, which interacts with the model. Then we send the desired magnet commands to amplifiers, which then send the current to the magnets, which then creates the magnetic field in the object. We track it with the camera, and then we send the state back to some state smoother so we can get decent velocity estimates as well as the position for our state. And this is how we can build a closed loop control architecture. The initial work on this let us do the first magnetic manipulation of non-magnetic objects. So here is first a numerical simulation where we can show 6 degree of freedom control. That's control the position and orientation. And that this environment is surrounded by 6 of these omni-magnets. And we are steering in a cube trajectory while holding a constant orientation. The second demonstration from this initial work was the first demonstration on the physical environment, where we have this sphere inside this raft, and we drive to corners, rotate in place, and draw a square, just to demonstrate that we can independently actuate different dimensions, even though the force and torques are always coupled. But our goal was arbitrary objects. Very few objects are actually solid metal spheres, even if we'd like more of them to be. That seemed easier. So our goal was, how can we, instead of measuring everything we know about a sphere, work with new objects? And so we have this very simple plan, which is, how can we use simple models for complex objects? Well, first, we're going to assume everything is a sphere. Second, we're going to use the recent observations to find the most likely sphere. And then we're going to pretend the most likely sphere is the correct sphere and use it for control. And so given a few of these known things, like the object, we have an equation for the object parameters, which think is conductivity and radius. We know what the control we sent. We know how to use the object parameters to compute a mass matrix. and we know the state in our wrench model, we can come up with a loss function that is how good does a set of parameters model the data, the observed accelerations, and find the best parameters under that loss function for a set of time trials. From there, we continue. So this is that was our original submission at RSS, and we added two kind of key additions. First, I'll go back, sorry. We added a regularization term. We said we'd like values to be around here in the parameter space, just as we'd like them to be the center of the parameter space, the most like obvious place that there's a lot of options to move around, and with some weightings for that. And we, instead of doing our desired force and torque, we switched the equation to be the controller to be thinking in terms of accelerations. So we use the mass function with its inverse to convert the expected force torques into expected accelerations with the desired accelerations to instead solve for the expected, just find the best acceleration. With this, we're able to show improved performance on these sort of simple objects. So here we're visualizing what sphere we think it was at each time step, where the color is the conductivity and the size is the actual size of the sphere we're estimating. And we see that we did quite a bit better with this than we had with the previous method. But it gets more interesting when we start to look at complex shapes. So this is this aluminum box. And what's interesting here is it's initialized quite poorly. All trials were initialized the same. But we can see quickly as they get to the first kind of corner of the trial that it's able to find useful parameters. And then for the rest of the trial, it does quite well manipulating this object. And we are modeling this mostly hollow object as a solid sphere. And we went a little further. We said, can we treat multiple objects as a single sphere? So this is 3 pieces of 80-20. And we're just observing it. We don't know what's inside. And we are able to manipulate this as a single solid copper sphere, or single solid metal sphere. We do the same thing with this, which is a pile of like 10 different pieces of copper just in a Ziploc bag put inside the boat. They're all touching. So whether the conductivity between them is important is unknown, whether they should be treated as multiple objects is unknown, but we're treating this as a single sphere, and we're able to control it quite well. But we actually see something I think quite interesting on this trial, which is this is 3 different trials. We see that there's really multiple possible objects that all control well. They all are representative of the motion we're going to see. So here in this upper right trial, we see it's this small orange sphere, and it's controlling well. In the bottom right trial, it started as a small orange sphere, and then it shifted to this larger yellow sphere. So that's less conductive, but larger. And then we see on the bottom left, it switches over as well to this other larger yellow sphere. So there's really here there's like 2 local minimum we can imagine, but there's probably a wider array of sufficiently useful parameters that might be useful to think about. This is one on a really complicated object where it's a bunch of pieces of aluminum bolted together that we think is something close to a CubeSat analog that you might see in space, or the closest we had laying around the lab. And this is actually our trickiest object. We can see here it's doing quite a bit of oscillation and rotation as we are moving through the trajectory. So we ended up showing that we actually could control the hardest objects we could come up with in our lab, that we could reasonably fit in our bench, and were reasonably conductive enough that we could control them at high speeds, or relatively high speeds. We were able to do everything we tried, and we wanted to start thinking about how can we make the problem harder so we can expand the capabilities of the system and understand more about what it would need to be if it were being deployed. So this is a trial. This is actually since the proposal was this work on how many magnets do we actually need to do 6-off control. So we had before the 6 magnet setup, and this is a regularization task. So the object starts here, and it's pulled into the origin, which is in the center of the 6 magnets. And we can see here we pull it from what is like 7 centimeters to the origin. We have the rotation come from about 1.5 radians to the origin smoothly following this cubic trajectory. And if we go down to 3 magnets, we get slightly bumpier. So the trajectory error is the error to the continuous trajectory, and it's a little larger. And if we actually go all the way down to 2 magnets, The error gets larger, but we still succeed in the task. It's just a little more oscillatory and doesn't follow it as closely. So we end up showing that we don't need nearly as many magnets as we originally picturing to do this experiment. I will say that we chose a speed for this scenario by choosing how long the trajectory would take, that they all could do. At higher speeds, the three magnets start to fail. They lose control of the object because we just have more control authority, so we can handle the higher, more dynamic speeds. But you can pick speeds where you can handle less and less magnets, and it's likely you'd rather go slow with a much cheaper system than go faster with a more complex one. So that kind of recaps this work on non-magnetic objects. And now we're going to go on to this other new work since my proposal, which is on using Stein variational gradient descent to build a distribution of possible objects. And then how can we use the whole distribution to improve our control? So first we'll cover what does that mean. So Stein variational gradient descent is this algorithm for variational inference where we have some goal distribution P, and our goal is to find the distribution Q that minimizes the KL divergence between P and Q. And Q is limited to there's some set big Q that you're searching over to find the best option. And your goal is to find Q star. One notable feature of Stein variational gradient descent is that it's gradient based. So you can see this iterative update here. How can we have some transform that takes in some points Z, or takes in the distribution Z, and produces a new distribution Z where you've added epsilon times phi, some function of Z. And you can think of this in like a gradient descent way. That would be like the negative derivative of the KL divergence. So if we start to think about how do we get that gradient of the KL divergence with respect to this transformation function, we get this expectation with a bunch of log likelihoods. We can evaluate it with the epsilon as 0, and we can make some limiting assumptions about what the space of Q we're searching along. And we end up getting this equation as the closed form solution to that, as long as we limit the search space to the kernelized Hilbert function, the functions that are mapped to the kernelized Hilbert function. So we get this expectation where it's the expectation of the kernel function times the gradient of the log of the probability plus the gradient of the kernel function itself. And the way we actually handle this in practice is we approximate this expectation with a series of particles. So we have a particle Z, or a particle Zi, and at iteration L, and you add this phi function times epsilon, and then you get iteration L plus 1. And we know that phi star, when you approximate this expectation, is just the average of the kernel function times the gradient of the log of the probability plus the gradient of the kernel function itself. And there's an important part to point out here, which is this right here is the kernel from a particle to every other particle times that other particle's gradient. So what we end up doing is you take a weighted average of the nearby particles' gradients. So they sort of share, I'm on a steep hill. I'm going to go down this hill. It looks like a great place to be. You guys should come join me. And then the other part, this derivative of the kernel function itself, is a repulsion term. So it says, you guys should join me down the hill, but like don't get too close. And the particles repel each other. So this is like quite intuitive, even though the initial math isn't quite obvious. It's quite intuitive where when you get out, how these two terms could turn into a useful distribution. It's been used in some recent robotics work. The idea being you take a cost function and you just take the exponential of the negative cost function, you have some normalizing constant, and now you have a probability distribution. Now, I will say we don't know how to sample from that probability distribution. We just define that it exists, and our goal is to build a distribution that looks like that one, but that we can sample. That's the kind of the big picture. We have a distribution that would be great if we could sample from it. How can we build an approximation that lets us? And so this has kind of been used in a couple cool ways. This one was building trajectories for motion planning tasks to avoid this obstacle and go to a goal where you get a distribution of possible trajectories. This is on some state estimation. And this last one will kind of build into what we're going to do instead is this built a distribution of possible object parameters. Specifically, they're talking about the instantaneous center of rotation. It's changing over time, and it's not necessarily a single fixed point, so they build a distribution over them. And so we like that idea, the idea of building a distribution of the possible system parameters, and we applied it to our object identification task. And so here is the loss function of our given some data set of our trajectories and the control values associated with them. Can we find what parameter is the best, would help us understand the motion the best? And that would be the mode of this distribution shown here in red. That's the single best parameter that would explain what we observed. But there's actually a lot of other parameters that are useful, and it's not obvious how you can make some local approximation that would capture the entire complexity of that distribution. So instead, we find these particles that approximate the distribution. And I'll point out one that I think is quite interesting. There's this very slim tail that curves around, and that point right there is still reasonably representative of what's going to happen, but the points nearby are not. So they spread out to be in this dense area, and they even continue all the way along this tail, but none of them are in this very unlikely blue region. So this is like a full distribution of how the experiments might go. And instead of having the control before was the best what action makes the best acceleration, we can think of doing this in expectation. What action in expectation under the full distribution of objects is going to perform the best? And because the expectation for the particles, they're all equally weighted, is just the weighted average of the acceleration error, we're able to find the control action that's the best in expectation, which actually does something quite cool. We came up with, in the numerical simulation, what we thought was the absolute worst case. So we're sort of worried, as objects are rotating in space, that the eddy currents induced on the different sides of an object as it's rotating, one side might be of different material, it might be, they might not be very rotationally symmetric. So there's this fear that as it rotates, the object's properties are going to change dramatically from our perspective. So what if in our simulator, every time step of the simulation, we pick a different object, and from some Gaussian distribution of possible objects, pick a different one every simulation step and use that for the simulator. And under this quite adversarial task, our original adaptive control framework fully loses control of the object. I'll show here that the position error goes from 0, because it's moving from 7 centimeters away, to 10 meters, and we just fully lose control. We accelerate it so much that we lose control, and it leaves the workspace where we were able to make any progress, and then starts rotating dramatically. So it was stable at no rotational velocity 7 centimeters away. And after attempting our original method, it's 10 meters away and spinning. But with this distribution, and thinking about an expectation under the distribution, we're able to still perform the task. It's definitely not as good as it was when we had a single known object parameters, but under this quite difficult version of our task, we're able to still control the object. So that work made us start thinking about, hey, this idea of Stein variational gradient descent is really cool. It applies to robotics in really interesting ways, but there isn't a way to apply constraints to it. And a lot of robotics tasks really only make sense if you can handle them with constrained optimization. So let's think about this distribution we would love to approximate. Remember, this is like a mythical distribution. We can just define it. So we're saying that, okay, with the same idea, we have the exponential of the negative cost function, but we'd like it only to be equal to that when the equality constraints are all 0. The inequality constraints are all less than 0. Each value is between some joint limits, some maximum and minimum value. If it's not all of those things, it should be 0 probability. So this function has no derivative at a lot of these places, so it would be quite tricky to approximate, but that's our goal. We would love this distribution. If we were sampling, that's when we'd like to sample from. We'd like good, feasible answers. So here's this sort of example dummy problem. This is from Nosedal and Wright. The function is x1 plus x2, and it has this this inequality constraint that x1 and x2 have to be within a circle with radius √2. So this is what this distribution looks like. So here is if you only do the naive thing and you only think about the exponential of the negative cost function, you get the most likely value is way in this corner. Really, it's infinitely far into this corner, but we'll bound it to this just so we can make it tractable. What we'd like is to stand from this distribution, which is rescaled to only be within the sphere. So we presented two methods to solve this. The first we call the Q method. And remember this equation where with the argmin of the KL divergence between Q and P, where Q is selected from the set big Q. The Q method is based off this idea where we want to limit what big Q is to only be distributions where every single particle is feasible. And luckily, constrained optimization has this idea that if you want to solve for this problem, all you need is the derivative of the KL divergence and the derivative of some additional term, L, which is just some constraint satisfaction term. And they have a bunch in constraint optimization, we have a bunch of these ideas of what it might be useful L's. And they're parameterized by some values theta. So we built this algorithm, which is update the particles with respect to the old value plus epsilon times the Stein term here, given a particle, minus the gradient of L for that single particle. This is saying if each particle has its own set of constraints, and if each particle is individually feasible, then the set that the distribution they come from is in big Q. And then every time this converges, we update the parameters as needed based off the level of constraint violation. Here's sort of an example of this running on this toy problem. So if we initialize, we'll initialize them all in the center just for consistency. These two different methods, the log barrier is an example of an L function, and the augment Lagrangian, they're characterized by the log barrier is overly conservative and then relaxes how conservative it is until the values reach the constraint. And it guarantees that values, as long as you initialize within the constraint, never exceed that constraint. It's called the barrier method for that reason. And the augment Lagrangian acts a little differently. It acts a little overly aggressive. So you can see how it passes the constraint, and then it increases how conservative it is until it pulls them back in. So here we can see the most likely values are along this edge, because that's the darkest color. But there's still some, as you spread out this distribution, along the inside of this circle. The alternative method we came up with, we call the P method. Its goal is to change P. How can we modify P so that it's easier and easier to approximate our goal distribution? So we create this P hat, which is the exponential of the negative cost function times the exponential of the negative, our same sort of L functions as before. And you can think of this, I had this example before of this trajectory optimization problem with Stein, where they had these obstacles that are just increasing in cost as you get closer and closer to some center. It's unclear the exact size of this obstacle, just that as you get closer and closer to the middle, it gets worse and worse. And that's incorporated as something like this. What we do is take a step further. We don't just take this update with our new Q hat or our new P hat that we've created. Every time this converges, we update the parameters and we make a new P hat. So our log barrier terms, our augment Lagrangian terms can be updating. Here's a similar example. And you'll note here, because the distribution itself is changing, we're recoloring the actual heat map. So here we initialize, and then we approximate this distribution, which is here. You know, it's in the deepest red here, and it's the surrounding red. Then it updates the parameters, and it pulls the distribution back to be tighter on the inequality constraint. And as we get tighter and tighter as the parameters update until it's so tight that all the particles are inside. Note that this equation is still continuous. There is non-zero values out here, but it is insignificant. It is outside the bounds. Here we're talking about like 1 to the negative 10, 1 to the negative 15, and that's sort of ballpark of likelihood, but all the particles themselves, the distribution we actually use, Q, is entirely inside the inequality constraint. So we tested this problem with a few of these different methods, with both the P and the Q, with our that simple problem against a ground truth distribution, which we made with rejection sampling. And we end up finding that either method, the augment Lagrangian finds a better approximation, presumably because it's just smoother, and the smoothness helps it just follow the trajectory better. And then the other important thing we end up finding is that the P method, because the particles communicate that they were in violation of the constraint, ends up doing a better job approximating the distribution because they don't get bunched up as much on the constraint. I'll go back to here. They're not nearly as bunched up along the constraint boundary as they were with the Q method. So it ends up doing a little better job in terms of the approximation. Yeah, that's just the two things I just said. So we came up with these three synthetic robotic tasks that all have constraints, and we want to demonstrate that we can solve them effectively with our method. So the first is this trajectory optimization with obstacle constraints. We would like to, with arbitrary precision, avoid these circular obstacles going from point A to point B and build a distribution of trajectories that all do that. We'd like them to be unique and efficient. We have this simple task where it's inverse kinematics, a classic optimization problem, but we have these additional constraints that there's on the object placement or pickup. You know, it's on a table, so we'd like to put additional constraints on things. And then this state estimation problem, where we have these semantic constraints. We know this object was on a table, so only limit your search to things that are on the table, which we encode as additional constraints. So first, we'll talk about the trajectory optimization. So our goal is the cost function is to minimize the squared acceleration, or the sum squared acceleration, and there's inequality constraints on the collisions. And we see here, this is for the first run of the internal optimizer with the Q method and augment Lagrangian. It starts wildly initialized. It finds trajectories from A to B, and they're all quite in collision. And as we improve the parameters iteratively, we get closer and closer to constraint boundaries. So you can see from here, like this particle, this trajectory right here, point because it's actually sort of important, is getting quite close to the this obstacle, but we're getting closer and closer to being feasible. And then finally, we get exactly feasible within the tolerances of just like machine tolerance that we care about. And they're all unique. What's sort of interesting is that we're pretty much spanning every possible homotopy class. There's a few you might imagine going fully around on this side, but we're pretty much spanning the full space of possible trajectories. And if we do something more traditional, if we just solve this problem independently 25 times, we would not get nearly as much diversity. Here we just get like 3 or 4 different options for the trajectory. They're cheaper in cost because they're much more straight, but we end up just getting, you can either go fully along the north, fully along the south, or kind of transition between those options. And so if you did this 25 times, you wouldn't get different options to choose from, but by jointly finding all 25 together and having this repulsive term, we get 25 different trajectories that we can then pick between in some way. Here's some quantitative results. We end up finding that the augment Lagrangian converges in much fewer steps than the other methods, but for both the P and the Q method. We do see this idea that the P method takes longer with all three of these solvers, which is interesting. So I guess there's some trade-offs there. We know that the Q method takes less iterations, but the P method does a slightly better job of approximation, which is maybe a design decision based off your task. We can go on to our next sort of synthetic task, which is this inverse kinematics over the SC3 Gaussian. So we have this error, which is in the pose, the error between a desired pose and the induced pose from some joint angles. And we take the matrix log to get this pose error, and with these two equality constraints. The first one is the pose error and the z-axis must be 0. So you can picture there's some table we'd like to pick something up off of or place something on. We have a desired pose we'd like to put it. And we're not super picky about the x and y, but the z needs to be exactly right because we're putting it on the table or picking it up off the table. The other constraint is this equality constraint that the z-axis has to be up. The object we're picking up or placing should be vertical, should be upright. And we can see what happens. So here I'll say I'm doing 50 particles of inverse kinematics here. I'm only showing 4, specifically the 4 that are the farthest from each other, just so that we can sort of visualize them easier. So this black is the desired transform. And we can see the blue and the red get quite close. The yellow and the brown end up quite far away. Specifically, the brown is stuck at joint limits. I'm pretty sure the yellow is to it, but I didn't check that one. The red, in a second, it'll snap on closer. So we'll let it just finish. So it gets quite close, but you see there's some error in theta, which we allow. It's just errors. The z-axis has to be in this case the red. The red axis has to be up. So we can think of this as the final at convergence. And here is, if we plot all the particles that we ran, how far away were they from the pose desired? And so the goal of the distribution would be, it's more likely to be close to the goal. but there's still some probability of being farther away. And here's the particles we showed. The brown is quite an outlier in position error. The red is quite an outlier in orientation error. Most of them are quite close. If instead we think about what happens if you have less particles, so we'll get rid of the plot and we'll see if you have 10 particles, they're all quite close. Because if you only have 10 particles to describe this distribution, you're very likely to have them all be sort of near the mode. It's only when you have more and more fidelity that you start to see these farther away points. The last task we're going to talk about is this state estimation with semantic constraints. So we have this task, we want to align a point cloud. So we have some known point cloud of an object, it's a soda can, and then we have some partial view of a room. In that room is a circular table, floor, and a soda can on top of the circular table. So we have this bound constraint that z has to be greater than 0. The object has to be above the table. There's an inequality constraint that the object has to be within the bounds of the circular table. And then this equality constraint that the object is upright. The goal here is to show that we have one of each of the kind of types of constraints. And here is at convergence. We can see this environment where there's all these floor points, and when we initialize quite wildly, they all pull into this area. And it's hard to see where the actual vertical points are of the soda can, where the ground truth the points are. What we can see is this bar right here of occlusion. And I'll point that one out because for the people on Zoom, right here, we can see a shadow of the occlusion of where the can was. So all those estimated cans are right around the actual position of the real can. And we can think about what that distribution looks like by doing a kernel density estimate. And we can see that we think we know the position within a few centimeters in all x, y, and z. The orientation, we get this quite interesting result, which is what we were hoping for, which is the rotation about z is flat approximately. And what we expect here is because the cylinder is rotationally symmetric and we maintained that there was the equality constraint that had to be vertical, the only rotation that's allowed is about z. And there's no reason to pick any of those values for that rotation. They're all equally likely to align the point cloud. So we get that the density is actually roughly equal along that entire span from negative pi to pi. If we do sort of like a less sophisticated method where we take away the constraints, but we initialize in the really extreme way we did, we initialized the rotations from negative pi to pi. So it could be arbitrary rotations. And ICP this is built on is really designed as a local method, but we're trying to treat it as a global method. If we use arbitrarily initialized particles without the constraints, we end up getting just a much poorer density. It thinks it's equally likely xy to be from a full meter. Yeah, so there's like a meter square that it could be. It just doesn't figure out where the object is. So by adding these semantic constraints, we're able to improve the performance of the algorithm because we can give it some known information, not just as a weak prior, but as a strong constraint. So there's a little bit of future work that we're still sort of working on in the lab. One of these is this ongoing project where we would really like to be able to do our magnetic experiments in 6 degrees of freedom in the real world. So trying to make an object that lets us control a sphere without the presence of gravity by submerging it in liquid, and submerging it in liquid and then making it neutrally buoyant in both position and in orientation. So there's no preferential orientation to the system. Is an ongoing thing that we're working on, and then as well as just generally working on making a more practical system. But this is where the research into how many magnets are necessary. How can we make things more powerful? How can we understand what it would require to put this in space someday? Because we would really like a tractor beam. Here's some of the publications that I've gone over. So it's the Nature paper we mentioned, this conference at RSS, recently accepted to IJRR, which is our big our big novel object. This interesting workshop on abusing a distribution of object parameters, and then our current in preparation RAL submission on constraints for robotic Stein variational gradient descent. I have some other publications in collaboration with members of Jake Abbott's lab, which brings us great to a final acknowledgement slide, which is my advisor, Tucker Hermans, my frequent collaborator, Jake Abbott, all my close friends and lab mates, and then Alan, who attended my wedding last year, and then some funding agencies, NSF, United States Space Force, and Rogue Space Systems.
You told me to be in that picture. I didn't want to be in that.
I know I did. It was funny to bring up.
It's good planning edits.
It's been in my mind for a year. Okay. Yeah, so any questions?
Yes.
Martin.
Yeah, so I think it's very cool. The space, debris, it's a problem. So I'm sure you can make your tractor beam work, right? You suck in that object, and then what do you do with that?
Well, the problem is mostly that these are small things that are all moving really quickly and they're spread out. If we grabbed 100 bolts and put them in a little bin, that'd be a much safer thing to avoid than 100 bolts that are crashed off of things in a net around that we have to each avoid individually. So if they're grouped, we can bring them with us. We can drop them down.
Where do you bring them? How do you drop them?
So if you slow an object down in orbit, it'll eventually go down to Earth and then likely burn up, depending on the size. If you speed an object up, it'll leave its stable orbit and likely fly away. I'm worried if I say too much, Zach will correct me for not knowing enough about space dynamics. So I will. I'll stay off from talking too much about it.
It's coming. Don't worry.
Our goal is to arrest the motion of an object to then have a secondary mechanism sort of deal with it. Yes, Ian in the back.
Are there plans to do testing where the object is already spinning? Because you showed that you can control the object, but
the answer is mostly a practical one. What we end up doing in our simulation, or where we have object with no velocity, we speed it up and then stop it, is effectively equivalent. It's difficult to start something with rotation and not like linear velocity. If it has linear velocity, by the time we start our experiment, it might have left our workspace. So we kind of are just like limited in our physical kind of apparatus. We have other experiments that I've not worked on, but some collaborators have, where they spin up an object in a 1 degree of freedom only rotation system, and then they're able to slow it down in that rotation. But that's constrained in every other axis, so it can only spin. And they're able to do things there, but it's mostly practical limitations on our part. But we think we've done equivalent tests. Noelle.
So you mentioned that your magnets do a pretty good job, but they're really slow.
Yeah.
When they're slow. Do you think that that is something that should be worked on before it's actually deployed? Or is it kind of one of those things where it's like, well, slow progress, cleaning up all the space debris is better than no progress?
Yes, there's a few answers to that. The first one is, as roboticists, anything that's not like a minute long feels really slow. So it ends up being like the experiments for most of them were 40 minutes long. The people we talk to that do things in space are like, no, that's super fast. They're talking about like how they can handle pieces, like how can we make a piece of debris that will come to Earth in 10 years? Can we make it come to Earth in 5 years instead? So they just think on these really long time scales. So what feels really slow to us is maybe not that slow to them. The other answer is it'll actually be a little easier to be faster in space because we can get free energy from much more efficient solar panels, and we could potentially have more powerful magnets. So there's some limitations on like what we can actually do in the lab. But if we're designing a physical system, a lot of it just like more power is more power. If we can use stronger magnets that are like physical magnets, we can have more powerful magnets that way. So there's some ways that it's not important, some ways it'll just sort of happen naturally. But it is sort of an ongoing question of, yeah, what can we do to make them faster? One of our kind of future works that Travis in the audience is working on is if we can turn multiple magnets on at once and we know how they collaborate, we can actually manipulate things much faster than if we have a single magnet and they take turns. Mohan had a question.
So you showed like you were able to manipulate a set of objects together, but then the transforms there are like rigid, but in reality they are like free floating. So
Yeah, so that that multiple objects was supposed to be as if there was a bunch of objects bolted together that are connected with non-conductive material. So if you had, or even just if you had, I don't know, a bunch of pieces of aluminum bolted together, or you had a piece of plastic with different pieces of aluminum on the piece of plastic, the plastic is going to act as a rigid transformation, but electrically they're going to be isolated. So that's sort of what we're mimicking there, not like a full cloud of different objects. We've done a little bit of work on what would happen if you have a full cloud of different objects, but one of the trickiest parts is the objects will want to hit each other. And that's something we haven't really looked into. But the force we end up creating does actually go out to all objects in the area. So you can create like an attractive force that pulls multiple objects into a central area, but they might all start to collide with each other. And so that wasn't kind of the point of what I was working on, which was a single object, but doing it really high quality manipulation. But there's some interesting things about how you could control like an entire cloud of objects at once. But the range ends up being the limiting factor there. Yishwan.
For your last project, what are the limitation and failure case?
The limitations in the failure case. So I didn't go into it here, but we ended up finding before that on the trajectory optimization problems that the Q method took more iterations. As you made the tasks more complicated, specifically this equality constraints, the P method actually just failed to converge. It was struggling to get the arbitrary constraint satisfaction that we required, because it was building a distribution near the constraint boundary, but the constraint boundary is some infinitely thin manifold, and not all the particles were actually on the boundary, on the manifold. But with the Q method, we were able to get all the particles to exactly land on that manifold. And so for this experiment, we only have results for the Q method, and we end up only running the ICP-based method with the Q method as well. So there's some part of this whole design decision of, would you rather have faster or more accurate distribution approximations, gets more and more complicated when you have harder problems. You're probably forced to pick the method that's faster with slightly less accurate approximations. And then I think Trent had a question. I'll go back to the publication pitch.
I was also curious about the last project for the trajectory optimization or the inverse kinematic stuff. What's the application of having extra bad solutions? Like generally, I think of you have to pick what your robot's actually going to do. So what is that?
Yes, that's a great question. So there's a few scenarios where you might want multiple solutions. I think one strikes a nerve with me is if you have a human in the loop and you would like them to help decide things, you don't just tell them, what should my joint angles be? That's a ridiculous question for a human to answer. But you could give them, here are 10 unique solutions that all do what I asked. Which one would you like? And they might go, this one's more pleasing for some reason, or future tasks, they might have good semantic reasons, but it's good for human selection. There are some tasks that's adversarial, where you don't just want to do the optimal solution over and over and over again, like optimal in terms of like speed. You might want to choose some stochastic policy. So having 10 reasonably good solutions that you can pick between randomly can be quite helpful in those cases. If there's one case that we're interested in, but we did not get to for this trajectory optimization one, where if you have a distribution of 10 trajectories and you're trying to execute one, you pick the best one, you're executing it, and your wheel slips and you end up drifting. There's kind of a few naive options you might do. Try to correct back on the trajectory you were executing. You might do kind of the model predictive control method and just stop momentarily and plan again. But this opens up another opportunity, which would be you could jump to another trajectory that you knew was unique, also good, that you accidentally fell onto. It's easier to continue on trajectory B than to correct back to trajectory A. So there's a few cases where you might have interesting ways you might want to use the distribution. At the worst case, it's still a very helpful global search strategy, because with optimization, finding the best, like an optimal solution by just initializing arbitrarily is unlikely to find a global minimum for these complex robotics problems. But if you initialize in a lot of places, even if a couple of those, the 50 particles end up at some joint limits, Luckily, that's not the only particle you initialized. If it was, you'd have a quite single pore solution. Here, we could limit ourselves to only having solutions that are sufficiently good through whatever metric you wanted. And at some point, we'll switch to private questions or public committee questions, however people want to do it.
Yeah, I think given the time, we should just move on to the private session unless there are more questions from the audience. Okay, well then we can thank Curtin again.
Yeah, I've seen someone do this, like they switch to a breakout